Good morning, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCC PSIIC. It's my pleasure to introduce today's speaker, Dr. Aditya Arun. He will be speaking on leveraging Wi-Fi for robust and resource-efficient SLAM. Dr. Aditya is a wireless system engineer at Skydio with a focus on building hardened communications and sensing systems in high contention environments. He graduated with his PhD from the University of California, San Diego, advised by Dinesh Varadia. His larger research vision is to incorporate Wi Fi and other wireless technologies as sensing modalities to improve the world of robotics and enable robotics to solve real world problems. His works have appeared in notable conferences including ICRA, Mobicom, Mobisys, Censis, and IMWT. His research interests span wireless sensing, robotics, signal processing, and networking. Previously, he completed his BS from the University of California, Berkeley. Outside his professional life, Aditya enjoys hiking, experimenting with new technologies, and mentoring young engineers. Before we move on to the talk, we would like to request our audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you feel free to unmute yourself and ask directly or type them in the chat box. We will relay your questions. Over to you, Aditya.
All right. Awesome. Thank you. Thank you for the introduction. And yeah, and as it was repeated, please feel free to ask me any questions in the middle of the talk. Yeah, and the chat box, I think, yeah, if you can help monitor that and relay the questions, that'd be very helpful. So yeah, so I will be presenting primarily my work during my PhD with Dinesh at UCSD. I graduated a few months back, actually. So and now I'm working for a company called Skydio. At the later part of this talk, I will give you a little bit more information about the company as well, some of the cool stuff that we're doing there as well. So my PhD, just to jump into it, so my PhD work was primarily looking at utilizing radio frequency signals like Wi-Fi, ultra wideband, and Bluetooth to actually sense the environment around us. And the core thought process was that as these signals propagate in the space, they will accrue certain information about the environment itself, and we can use that to figure out the locations of various devices, be it robots, users, or UWB tags, or any other such devices. So with that, my work has primarily been towards enabling the future of many of the smart indoor applications that we think of today. To name a few, you can think of the next generation factories, which are actuated and autonomous. You can also think about building digital twins for these same factories, where you can actually understand many intricate portions of this environment by building accurate twins in the digital domain. You can also think about it from an entertainment perspective, where you have spatial audio systems which actually direct 3D audio to users in a space. Or smart indoor spaces can also encompass multi-user VR setups where, very similar to the remote talk I'm giving you right now, we could all be transported, instead of each of us being in our own rooms, we could all be transported into a shared virtual reality. And moreover, for people who are co-located in the same space, they can be more easily transported into shared spaces as well with multi-user VR. On the other side of these systems, you have the push of indoor robotics for safety purposes, for cleaning, and for various other industrial tasks. And finally, you see that these robots are making their way into our homes as well for be it vacuum cleaner robots or just personal robots for companionship. And finally, more relevant to some of the work I'm doing at Skydio, we're also seeing a major push of using robots and drones for many mapping and surveillance applications in indoor and in many indoor environments. And what I find is across this diverse range of applications, all the way from factories to mapping indoor spaces. The location of key assets in the environment, be it the locations of boxes, the locations of people, the locations of robots, plays a very fundamental role in enabling these future uh, smart indoor applications. And with that, kind of looking at this broad set of applications, I've been able to break it down into two broad categories. On one side, you have a room scale application like the multi-user VR applications, or the streaming of 3D spatial audio to users. And the primary requirement here is to have centimeter scale localization, but in small confined environments. On the other hand, you have many applications that require building scale localization capability. And some of it, one of the first ones that come to mind is a simple application of a surveillance robot patrolling an environment. This robot needs to have centimeter scale accuracy, tens of centimeter scale in some cases is all right. But it needs to have this accuracy throughout the building in GPS denied environments, and it should be able to map itself and plan a route to reach the various parts of the space itself. And over and above some of these accuracy requirements, there are three core requirements across both of these systems. The first one being it has to be robust to many of the indoor challenges in indoor spaces, primary of which is GPS denial. The second is it has to be resource efficient, and by resource efficient, I mean it has to be deployable on small compute form factors. It has to be deployable on memory constrained devices. It has to also be power efficient if possible, so that you can ensure long battery operation. And finally, it has to be privacy preserving as well. And this has been a more recent requirement with some of the kind of sensitivities regarding information privacy. And it is further made important by the fact that many of these robots actually are finding their way into our homes. So with that, my PhD work looked at utilizing RF signals, like I mentioned, UWB, Wi-Fi, BLE, to actually provide this location information to many of the devices. And what we found through these works is that RF provides a great way to do privacy preserving, resource efficient, and accurate location estimation in many of the indoor applications. And each of these works sort of targeted one of the applications that I told you about a few minutes back. So on the room scale end, two of my works utilized UWB signals, XR-lock and U-lock. They utilized UWB signals to provide centimeter scale localization accuracy and millimeter scale tracking accuracy to UWB tags in large scale environments. Moreover, during COVID itself, what we started realizing is many of the existent contact tracing apps, which primarily utilized RSSI, primarily utilize the presence of a BLE beacon to determine if there was a contact. We found that that had a very high amount of false positive rates. So with that, kind of we designed Bluebill, which utilized BLE signals RSSI, and we developed an ML model to sort of improve the false positive rates existent in contact tracing applications. Interestingly, actually, some of this work was we actually later prototyped and tested it out a little bit with Arogya Setu in India as well, which was pretty cool. On the other hand, with the building scale localization, a lot of my work has primarily utilized Wi-Fi signals, as that is the most prevalent indoor wireless area network today. In two of the older papers, DLock and LockApp, we tackled the problems of actually deploying user-based localization systems in large-scale environments. And in more recent works, P2 SLAM and WAIS, we actually looked at extending the robot sensor stack, which currently includes cameras and LiDARs, to actually incorporate a Wi-Fi radio as a sensor as well. And again, more recently, which this work is under submission, but we are also looking at how can we kind of look at the other part of this problem, which is also preserving privacy to the users from being localized. So this is again a more of a security and privacy concern, in that the past 10 years again have improved Wi-Fi localization systems to the extent that I can localize users without their consent in many public spaces. So we are looking at the reverse problem of, are there ways users can actually protect themselves from being localized against this non-consensual means. However, in this talk, rather, I would want to concentrate primarily on two of my works, which looked at extending Wi-Fi radios as sensors, and tell you a little bit more about why we did that and how we did that, and some of the advantages of kind of going down that route. And after that, I would like to close out the talk with a little bit more information about Skydio and how all of this sort of fits with some of the work they're potentially doing there. So with that, let's jump into the core of the talk itself. And when we think about robots, many of these robots might come to your mind. These are very famous, available in the market robots. And the first thing that will catch your eye is the fact that all of these robots are equipped with cameras or some sort of visual sensing. They could be 3D cameras, stereo vision cameras, LiDARs, just normal monocular vision. And the primary thought process is that these cameras can help find landmarks, unique landmarks in the environment. And the tracking of these landmarks will help the robot actually navigate its space. However, what would happen, in indoor spaces like the one I just pulled up on the screen? The first thing that sort of jumps out at you is the fact that it's a very bland environment, which is lacking any visual features. And oftentimes, you will find these kind of environments in in buildings, and robots find it extremely hard to actually navigate in these spaces because they don't have those visual landmarks I mentioned previously. And this problem actually continues to become even harder in situations of dynamic lighting, or if it is dark in the environment itself. So the core problem that we are looking at is, can we utilize a sensor modality that can actually bring back diversity in many of these monotonous spaces where robots can actually get lost? And touching back again to the previous properties of resource efficiency and privacy, we are also seeing that many of the robots that are going to be deployed are becoming smaller and more resource constrained, be it drones that are seeking to map an environment effectively, or VR and AR headsets which have a limited battery life and memory and resource capacities. And on the other hand, again, you have many of these robots coming into our homes, which again begs the question of privacy and the security of when these robots are actually operating in our spaces. So again, in addition to bringing back diversity, we ask, are there sensors that can also improve the resource efficiency of localization and mapping systems, and also make them more privacy sensitive? With that, I would like to dig a little bit deeper into this aspect of resource intensiveness and why that is such a challenge today. So to understand this, let's go back a little bit to how a robot actually maps its environment. So in this example, what I'm showing you is in the green line, the robot has taken a trajectory, and it has started and stopped at the same point, and you can see that the trajectory has made a nice loop. which indicates the reality. But oftentimes what happens is as these robots move in the environment, they accrue a lot of drift and there's a lot of integration errors in their sensors, which actually leads to a trajectory prediction which might look like this on the right side instead. And what you can clearly see here is that this loop is not closed. The robot doesn't believe that it has come back to its starting point. So to actually circumvent some of these challenges, aptly named loop closure constraints, as I have highlighted in blue, are applied to actually tie the trajectory back together. And to find these loop closure constraints, very simple thought process is utilized. If my robot revisits an environment, it must see the same landmarks and the same things it saw previously. So in this toy example, I'm just showcasing the fact that a potted plant that was seen at the start of the trajectory, and the same potted plant was seen at the end of the trajectory. And this means that the robot has actually revisited the same space, and you can actually apply this loop closure constraint. However, two things may jump out at you when you think about this. The first is that to find these loop closure constraints, a robot actually has to look back in its memory, look back in its past, and find all of those places where this similarity exists. So this can actually be a very resource-intensive process because I'm storing all of these frames in my memory, and for each frame, I might potentially be doing this comparative search over my past. And furthermore, what we also see is depending on how much the trajectory has drifted away between these loop closures, applying these corrections can accrue a significant amount of optimization cost as well. And this is, and both of these points, which I mentioned, is assuming that these loop closures are even happening correctly. So on the in the worst case scenarios in many of the indoor spaces, what we also observe is that these loop closures can wholly fail, which can lead to completely inconsistent trajectory estimates as well. So with this kind of background of loop closures and really the requirement of these systems, it is clear to see that current SLAM algorithms, SLAM is simultaneous localization and mapping. Current SLAM algorithms are heavily dependent on these loop closure systems, which actually are the same systems that may be holding them back in terms of resource efficiency and reliability. Yeah. So with that kind of following some of the previous work we did in Wi-Fi localization, what we started observing is the Wi-Fi signals that a robot receives in the space can actually be extremely diverse. So to get an understanding of this, let's imagine a robot is actually walking down or driving down this corridor, and take a look at what the Wi-Fi radio actually sees as it drives down this corridor. So these images are visualizing what the radio is seeing. I will give you a little bit more information about these images in a little bit. But the first thing that is very apparent is that these images are extremely diverse. And if we can somehow utilize the information in these images, we can bring back the diversity in these monotonous environments. So my work in P2SLAM and WAIS primarily looked at extending the system and using this core thought process to actually build Wi-Fi radios as a code sensing modality for wheeled robots itself. So with that, I want to just show you a quick video. So there's no audio in this. So it's just going to give you a little bit more information about how the robot actually traverses an environment. The image captured by the robot's camera is in the bottom right. You will see the robot trajectory appear in blue on the grids. And what it will also do is because this robot is capturing Wi-Fi signals, the access points, the Wi-Fi access points in the environment act as key landmarks for this robot itself. So it will actually discover these access points in the environment and actually place them in the space and use the locations and use these access points themselves as the RF landmarks to correct for the trajectory. On the left side, you will see some of the CPU and the memory consumption statistics, but we will get back to that later. So yeah, so I'll let this video play out, but you see how the access points are localized and optimized into the right location. And what you will also see is on the left side, whenever these access points are added, there is a slight jump in the memory and the compute consumption as additional optimization is being done to actually figure out their locations. So in this part, you will see something interesting where as the robot revisits an access point, it actually uses some of the Wi-Fi image information, which I showed you earlier, to actually correct for the drifts that the odometry would have predicted otherwise. So you will see another example of this here. So again, to repeat, this was a video that was sped up by about 15 times. But this data set was the robot drove about 400 meters in this environment, and uh, it was collected over a 25-minute period. So I will pause this here, but this video is available online for you guys to take a look at. But the bottom line is that not only does adding these Wi-Fi radios as sensors improve the reliability of these robot systems, but it also actually improves the resource efficiency, both the memory and compute, by over 4 times as compared to traditional Visual SLAM systems, traditional systems that purely use cameras and LiDARs. So with that, let's actually step back and understand what those images actually were. And to get a better understanding of it, let's look at a simplified one. And let's put a cartoon of the robot and an access point in the environment. So as the robot actually approaches this access point, it receives a signal from this radio. And this image is showing you nothing but the probability profile of the angle of arrival of this received signal and the relative distance it has traveled over the air itself. And the peak of the profile, as highlighted by the star, in fact shows the most likely angle of arrival or bearing estimate in this scenario. So by utilizing this AOA information, this angle of arrival information, we can actually just treat these access points as RF landmarks in the environment, very similar to how cameras treat the pixel locations of unique landmarks, unique visual landmarks. If you think about it, pixel locations are nothing but the azimuth and elevation with respect to the camera lens, right? So this is a very similar thought process, but we're extending it to this RF domain. However, with this core thought process, when we actually take these radios and put them in the real world, these images don't look so clean, but they look more like this. And the reason for this is there is a lot of reflections in the environment itself, which can create these spurious peaks and ambiguities in the space. So to actually to actually find out the bearing estimate from these ambiguous peaks, what we do very simply is make an observation that the primary signal, which is arriving, the solid line in this case, is the line of sight signal which travels the least distance in the environment itself. So with that, we can actually look at the x-axis of distance traveled to understand and pick out the right peak in this environment itself. However, Apart from multipath itself, one of the key properties of Wi-Fi signal is that a lot of times you can receive it even when the direct path is blocked in the environment itself. And this is great for Wi-Fi signals because you can get very good connectivity in an indoor environment. But this is really bad for our sensing purposes because this can mean that we will estimate inaccurate bearing measurements, inaccurate and inconsistent bearing measurements. So to actually reject some of these packets that we receive, what we observe is when this direct path is blocked, the packets we receive have much lower signal strength, and we can utilize we can just simply threshold based on the signal strength indicator of RSSI to reject some of these packets. And to be more precise here, I'm just showing you a histogram really quickly of some of the bearing errors when we look at all the packets in the environment, as opposed to the bearing errors of the filtered strongest packets in the space. And what we can see is that, of course, you have fewer number of measurements in the blue curve, but those few measurements are much more accurate, and that is what matters. Because as we look towards feeding this system into an optimization framework, it is really key that we maintain a high quality of measurements into the system as opposed to a large quantity of them itself. And just to skip over, just to go back to some of the slides I skipped over. So these images we generate by utilizing the channel state information of the Wi-Fi signal itself. And the channel state information is telling you the signal's magnitude and phase properties across the multiple receive antennas that it is equipped with, and across the multiple frequencies that the signal is transmitted over. So you can take a 2D Fourier transform across this antenna and frequency domain to actually arrive at this angle of arrival or bearing and distance domain. The information of some of these things are actually in some of the previous works. We can take a look at BLOC, which is the work from my co-author, Roshan, to understand a little bit more about this. But I'm happy to answer any questions you guys might have. So with that, kind of with a lot of some of this core thought process in place, we developed WAIS, which stands for Wi-Fi Assisted Indoor SLAM. And the primary thought process behind this was to integrate Wi-Fi sensors with existing SLAM systems that utilize cameras, IMUs, and LiDARs. So to do this, we take in erroneous odometry, visual inertial odometry, based on either camera IMUs or just pure LiDARs or just pure wheel odometry. And we feed it into WAIS's optimization framework, which takes in as input the Wi-Fi measurements, the angle of arrival measurements we spoke about, and it builds an optimization framework to actually incorporate these measurements. And it outputs in real time corrected odometry, which can then serve end applications such as mapping, navigation, or space exploration, indoor exploration. So with that, I want to just give you like a high level thought process of all the evaluations that went into building this system, and I can open up the floor for some more questions for people to ask, and I can then jump back into giving you a little bit more information about what I'm currently doing. So to evaluate WAIS, the primary deliverable, like I mentioned to you, was its ability to interface with existing SLAM systems. So to test this out, we integrated it with a LiDAR inertial odometry system called Cartographer, and also a visual inertial odometry system called Chimera. Both of these systems come with their loop closure modules turned on. So in the case of Cartographer, you have the scan matcher that actually finds those loop closure matches I spoke about. And in Chimera, you have independent loop closure module. So the primary goal of WAIS is to actually circumvent the use of these loop closures and utilize the Wi-Fi bearing information instead. So to do that, when we feed the inertial odometry estimates into WAIS, we actually turn off the scan matcher and the loop closure systems, and then we measure the trajectory provided by WAIS. And of course, we compare this against the baseline of cartographer and Chimera. And we do extensive amount of indoor testing. The first one is a 35 by 30 meter environment. This is the same environment I showed you earlier in the video. Here we are, there's three APs deployed about 10 meters apart. We try to deploy them in extremely realistic scenarios. They're deployed near the ceiling, as you can see from the photos. And again, we drove about 400 meters in this environment. Uh, two other data sets were collected in a similar office environment, 25 by 30 meters. Again, with similar AP densities, deployment scenarios. And finally, one data set was collected in a larger 50 by 40 meter environment, which had more of these open corridors and bland looking featureless spaces. So overall, through these four data sets, we traversed a cumulative of 12, over 1,200 meters, and the total time of data set collection was about 2 hours. So with that, I want to just show you some key results from the paper itself, but I will put up a QR code later on, which links you guys to the paper and the GitHub and everything. So first off, we look at the median translation error across these four data sets. I'm showing you the median translation error of cartographer. And when we take this LiDAR inertial odometry without the scan matcher from cartographer, feed it into WAIS, and do the Wi-Fi-based optimization, and we look at the locations, we can see that these locations are comparable accuracy to what cartographer provides. And when we look at, again, looking at the qualitative graph, quantitatively, they're very similar as well. But what we can see is when we look at the visual inertial performance as well, we can see that Chimera follows the ground truth trajectory quite closely, although there are a few places where it drifts away from ground truth. And we can see a similar optimized performance of WAIS as well. However, and this is really just setting up the stage to showcase the fact that Wi-Fi-based integrations do work, and they work consistently, and they work well in realistic environments. But the real kicker of incorporating Wi-Fi radios is the resource efficiency that they provide. So here I'm just showing you the RAM usage in gigabytes and the CPU usage as a percentage of cores. So the first in the orange, you can just see Chimera's memory and compute usage. On the memory side, the first thing you notice is it starts up with a large amount of reserved memory. This is primarily to actually store all of the loop closure frames and a lot of the visual information that it needs to apply the corrections. And you can see that this memory actually grows over time as the robot actually traverses the environment. On the other hand, when I actually put down the memory consumption of WAIS, you can see that at the startup, it is almost more than 3 times lower amount of startup cost. And not only that, but you see that it is almost 3 times less memory usage per second. Like the increase of memory is almost 3 times less. And this is primarily because we are not using loop closure modules to actually apply these corrections. So you can see a much more efficient memory performance here. Again, stepping away from requiring those loop closure searches also gives us almost a 2 times improvement in the compute usage as well over this time period. And we kind of see similar performances when we compare it with Cartographer as well. So on the top plot, I'm showing you the RAM usage of Cartographer as compared to WAIS. And we see something interesting here, which is that the memory usage of Cartographer and WAIS are actually fairly similar. And the primary reason for this is Cartographer utilizes 2D LiDAR scans to actually map the environment. And these scans are extremely low memory. They consume very low memory because there's a very sparse representation of the space itself. But this sparsity is actually a double-edged sword, because when you need to actually do scan matching and figure out which of the past scans match my current scan, it takes a lot more effort. And this effort is evident in the CPU usage of Cartographer as compared to as compared to WAIS itself, where you can see almost a 4 times reduction in CPU usage by WAIS. So the bottom line through these results is the fact that Wi-Fi radios provide really the best of both worlds in terms of uh, optimized memory performance and optimized resource performance, whilst also providing you improved resiliency to many of the challenges in indoor spaces itself. So yeah, and so with that, I would like to just leave the slide up here with some key takeaways. P2SLAM. So P2SLAM was the precursor of this, where we studied a lot of the sensor characteristics itself, and WAIS looked at building the system. But the GitHub link here should take the QR code here should take you to the website to give more information. But WAIS primarily looks at integrating Wi-Fi radios as a sensor into the real-time SLAM stacks of robots. It provides a 4 times improvement in resource consumption over visual-based systems. And finally, we actually open source the ROS nodes that were used to stream, calibrate, and integrate this Wi-Fi data into the robotic stack. So yeah, with that, I can pause for a bit for you guys to ask some questions. I have about 20 more minutes, so I'm happy to take some questions. I have 10 more minutes of maybe presentation. Wanted to give you a little bit more information about Skydio itself. But yeah, happy to take any questions. All right. Okay. So I guess I can just like move on. So anyway, so yeah, I'm really excited to actually I just saw Pompa, who is one of the leads in Skydio's India team, is actually on call as well. So I'm really excited to kind of tell you some of this. Hi, Pompa. So yeah, I recently joined this company, and I just found it to be a great fit with many of the work that I presented here, and I wanted to tell you guys a little bit more about it. And really, I think smart folks like you is where what we need, and kind of to continue building some of this technology going forward. So Skydio is it's primarily a drone manufacturer. We look at building eyes in the sky for the defense industry, for the public safety and utilities industry, with the primary goal of improving the safety and the productivity of users in the world. So Skydio is fully US based, operations. With we have our own manufacturing in the Bay Area as well, and we provide drones to all sorts of industries. And in fact, I think more recently we are actually providing some drones to India as well. And yeah, and in this brief talk, I'm not going to delve into all of these. I just wanted to give you a little bit more information about some of the more recent drones that we are building, which is the X10, which was announced a few months back. And I just wanted to give you guys a little bit more information about the hardware platform itself, as I know many of you guys are hardware engineers here. So with that, the Extend drone is primarily targeted towards enterprise and defense applications. It has a single NVIDIA core along with a Qualcomm core, which provides it extremely capable AI computing power, as well as extremely capable communication uh, capabilities. Yeah. In addition to that, we have really retrofitted this Extend with a much better camera, incorporating infrared and a 4K camera, and we have provided it multiple add-ons to really improve the modularity of the system itself. So yeah, so with that, as I mentioned, it comes with the NVIDIA Orin GPU, as well as the Qualcomm Snapdragon, and these two guys play hand in hand to provide many of the autonomy and the navigation capabilities that Skydio is really famous for. In addition to that, I think, like I mentioned, we build drones that essentially behave as eyes in the sky. So, which means that we need to have really good cameras that can give our customers very good situational awareness. So that means that we have multiple navigation cameras that can provide a 360-degree view to our customers, and that improves the situational awareness. And in addition to that, we have actually so these nav cameras can provide you extremely good visibility of the environment. And in addition to that, we have actually retrofitted this camera with a 4K a drone with a 4K camera with extremely, I think, almost 10x amount of zoom. Correct me if I'm wrong here, Pampa. As well as multiple infrared sensors and emitters to provide, additional sensing capabilities outside of the visual spectrum as well. So yeah, so with that, I think we are, extensively hiring to kind of continue to improve many of these drone packages. I know many of you guys are in the communication space in the talk today. We are continuing to hire in that space to sort of really improve the capabilities of this drone as they start flying in extremely contentious environments, be it in front lines of Ukraine, or even in spaces like New York, where there's a high level of congestion. So ensuring that these drones operate reliably, operate consistently in these environments continues to be a challenge, which we are looking to solve and solve better. So yeah, with that, I'm happy to again take some more questions, or discuss any ideas or anything else you guys have.
Thank you, Aditya, for a very informative talk. Please ask if there are any questions.
So if you guys don't have any questions, maybe I can ask a few questions. So I'm curious. So CNI, what do you guys do there?
Okay, so in CNI, CNI actually has professors and students. I am one of the students at IISc, and some other technical staff. So at CNI, other than research, we organize seminars, we organize hackathon, and also some other activities we do at CNI. We also organize summer school and in every June to July months, we also organize CNI summer school. So there are many activities going on in CNI.
Nice. So what is some of the research that you guys are like focusing on right now?
So I work on caching. Especially I work on this. I don't know if you heard of this term, age of version, where you look at. There was earlier age of information. Now it is age of version, because it doesn't matter how long you have the old version, it matters that how many updates have happened since you have fetched the old version. So I work on fresh caching, and earlier I had a paper on edge computing also. So there you so there you have your base station. It has a uh, what is it? It has a MEC server, uh, and instead of serving the services at the cloud, you want to serve at the close proximity to avoid latency. So, but MEC server has its own limited resources and all. So how and so there we assume that the services are come to users, and then user decide whether to send to MEC server or to send to the cloud. And there is a queuing decisions. I mean, there is a queue at both the users and the MEC server, and the decisions are involved to minimize the to maximize the throughput of the whole system.
Okay, interesting. Okay, that's pretty cool. Yeah, and I think some of the caching work is, yeah, I think it's quite related to some of the other loop closure stuff I mentioned as well, right? Because at the end of the day, a lot of the work that looks at actually improving these loop closure systems actually look at how can I better access the relevant visual information, and
Yes, yes,
the more like how can I cache it in a better way, right?
correct,
But
correct.
then, yeah, but we look at how can we just circumvent it altogether. So,
Yes,
but that said, I think very relevant work. You will find it. There's a lot of work that just looks at how can I improve loop closure systems, and caching
yes.
is one of them. Yeah,
Thank you. It's very nice to interact with you.
yeah, of course.
So,
Pampa, you're muted.
Yeah, I am muted. Sorry about that. One question I have is, when you conduct these seminars, who are your audience primarily?
oh, okay. Our audience is mainly from our institute, from ECS division. So
Mm-hmm.
it can be faculties from ECS division, from like CSA or ECE or CDS. I mean, data science departments. So, and some of our audience from outside also. So, who has graduated from IISc now or at
Mm-hmm.
different places. And we also try to. We have another Google group where
Mm-hmm.
there are audiences from triple IITs, another IITs also. So they also join our seminars depending upon their interest.
Okay, okay, understood. Yeah, so if you have any questions on Skydio, I mean, reach out to any of us. I am here in Bangalore, so if you want to get in touch with us, please do so.
Okay. Okay. Thank you so much.
Yeah. All right. Awesome. If there's no more questions, I might head to sleep. It's
Yeah.
I had a
So if
tiring
there are
day.
no
So
more questions, we can close this session. Thank you again, Aditya, and
yeah.
have a good day.
Yeah, and thank you, Pompa, for attending, and yeah,
And
it
no
was
problem
great.
at all. Hey,
All
thanks,
right.
thanks,
See you
Aditya.
guys.
Bye.